This will be lesson 5 of unit 8. In this unit we've been talking about empirical formulas, which are formulas for compounds derived from empirical or laboratory data. Now, we've defined empirical formulas in this way. An empirical formula shows the smallest whole number ratio of atoms in a compound. So this is essentially the lowest reduced version of the formula. So in this case you see CH3 as the empirical formula. This is because you cannot reduce it any further. It's as low as it can go. There's a 1 and a 3. Now, this is not the real formula of the compound though. The real formula is called the molecular formula. Molecular formula shows the formula as it actually exists. So the example here is C2H6. Now both of these formulas refer to the same compound, and the compound is this. This compound is called ethane. And it has 2 carbons and 6 hydrogens. The black are carbon and the white are oxygens. Now if you take this ratio 2 to 6 and reduce it, you'll get down to 1 and 3. And so far we've been calculating these empirical formulas. But it's important to say that empirical formulas are not the real formulas. So there's one more step we need to do in this chapter, and that is to show you how to calculate molecular formulas, the real formulas of the compounds. So this slide gives another example in order for us to understand the difference. Here we have 2 molecules, both ethene and cyclopropane. By the way, these molecules are from organic chemistry. Organic chem. They have the same empirical formulas, but are very different compounds. So if you take a look, this molecule, there are 2 carbons. Again, these are carbons, and these in this case are hydrogens. In the case on the left, you have 2 carbons and 4 hydrogens. In the case on the right, you have 1, 2, 3 carbons, 1, 2, 3, 4, 5, 6 hydrogens. But if you reduce both of these down, they both reduce down to CH2. And this one to CH2. And to reduce it, you would divide as much as you can until you cannot divide any longer. So notice the empirical formulas are the same, but the compounds are different. This means the empirical formula is not enough. There are actually many, many compounds that have the same exact empirical formula, but they indeed are different compounds. So how do we find the next formula, the molecular formula? Well, the molecular formula is simply a multiple of the empirical formula. A multiple means it's 2 times bigger, it can be 3 times bigger, 4 times bigger, a whole number multiple. I mean, it could be 7 times bigger. And in order to find this multiple, how many times bigger it is, you compare the 2 molecular masses. You take the mass of the molecular formula and the mass of the empirical formula, and you divide them. So when you divide the bigger number, say 10, by the smaller number, say 5, you get the number 2. And this 2 is the multiple. This means now that the molecular formula is 2 times bigger than the empirical. So if the empirical was CH2, the molecular now times 2 is C2H4. So the multiple simply compares the formula of the real mass against the formula of the, real mass against the empirical mass. And you always do bigger number versus smaller. That way you get a whole number that's bigger than 1. So why don't we try an example of this, see how it applies to our compounds. And the example is this. The empirical formula is BH3. Find the molecular formula if the molecular mass is 27.67. So we want to first find our multiple. Our multiple is simply the molecular mass versus the empirical mass. Now, our molecular mass is 2767. Our empirical mass comes from BH3. So we have boron. If you take a look at boron, it has a mass of 1081. We have 3 hydrogens. Each hydrogen has a mass of 101. Now if we total this up, we got 4 here, we got an 8, we got a 3 here, 13.84. So that's what goes down here, 13.84. And you can probably already see that the empirical formula is half as big, or the molecular formula is 2 times as big. In fact, if you divide the two, you will get about 2. And 2 then is the multiple, which means our formula is not BH3, but multiplied by 2, B2H6. So this is now the molecular formula. Not bad. Hopefully that was pretty easy. Now, how do we get, you say, well, how will we get these numbers? Because the empirical formula numbers came from experiment. Well, this molecular mass also comes from another experiment. You would conduct an experiment that tells you roughly how much the real formula weighs, and since you determine the empirical formula, you can derive the molecular formula from there. So take a look at this and try a problem of your own. Very similar. And then let's go ahead and put it all together. This last example that we do, we'll put together the idea of empirical and molecular formula. So here's the problem. A compound contains 5.927% hydrogen and 94.074% oxygen. Has a molar mass of 34,015. So this is going to be our molecular formula's mass. Find both the empirical and molecular formulas. So let's go ahead and apply the 4 steps of the poem to first find the empirical formula. And those steps, remember, were percent to mass. So we first convert these percents to grams. Simple as that. So we have 5.927 grams of hydrogen. We have 94.074 grams of oxygen. Percent to mass. Second step said mass to mole. So we'll convert both of these into moles, and we do so by putting grams at the bottom, 1 mole on top. Grams at the bottom, 1 mole on top. We have grams of hydrogen, grams of oxygen. The grams of hydrogen is 1.01. The grams of oxygen is 16.00. Hopefully you remember where these numbers come from. And now if we divide, go ahead and do this division with me. 5.927 divided by 1.01. We'll get ourselves 5.868. Now remember, it's important to keep significant figures. So if you have 4 here, keep at least 4. Don't round until the very end. If we divide the oxygen, we have 94.074 over 16. That gives us 5.879, or 5.880 if you round. This is moles of hydrogen. This is moles of oxygen. That's step 2. Step 3, remember, was divide by small. So we would divide both of these by the smallest of the 2. Now, the smallest of the 2 here is this one, 5.868. 5.868. And what you see essentially is these numbers are the same, which means that you get 1 mole of hydrogen, 1 mole of oxygen. Now, this is one of those cases in which you don't need to do the last step. If these numbers were not whole numbers, or were not very close to whole numbers, then you would need to multiply to whole. But because if you take a look, if you do the bottom calculation, the 5.880 divided by 5.860 gives you 1.00, which is pretty close. Remember, if you're just within maybe a tenth or so, you can keep it a whole number, which means our empirical formula is just OH, or HO. I'll go and put OH, as there are no O's in chemistry. Okay. OH, here we are. So now this is not the full formula, this is just the empirical formula. What we're saying is this is the ratio of the formula of the 2 atoms. There is no compound by itself that actually exists that's OH. There is no compound called OH. There's a polyatomic ion called OH that's hydroxide, but it has a charge, -1 charge. But this compound does not exist. Now we have to find the molecular formula, and we're given this mass. So let's find our multiple. And the multiple was, you take the 2 different masses and you divide them by each other. So you take the bigger mass, which is 34,015, divided by the smaller mass. Now the smaller mass is the mass of OH. The mass here, we have 1600 for oxygen, we have 101 for hydrogen. That gives us 1701. So we'll put 17.01 down here. Now you can see in this case that the multiple gets us 2. So again, the empirical formula is 2 times smaller, or the molecular formula is 2 times bigger, which means our real formula is not OH, our real formula is O2H2. And actually, hydrogen is written first usually, so this is H2O2, the formula for something called hydrogen peroxide. Hydrogen peroxide. We've used this compound before, and you have a bunch of it probably at your house. It's in those brown bottles. So I know it looks like a lot of work, but pretty simple. You find the empirical formula, which we found to be OH. Then you compare its mass to the molecular formula's mass. And however many times the molecular formula mass is bigger, that is how many times the formula is bigger. And that's how we arrived at the molecular formula. Hopefully that made sense. Go ahead and try this last example on your own, and we will do a lot of practice of this concept in class.